Good afternoon, everyone. Thank you for coming. Today we have Professor Dong from Sydney University. So Professor Dong is the head of the School of Electrical and Information Engineering in Sydney Uni, also the chair of a research cluster in the Faculty of Engineering that deals with clean energy. He's part of the ARC panel of experts. He's editor of a few of the major IEEE journals. And he also has quite large industrial experience. So from all this one, you understand that probably is the best person to speak with us about the grid and what is the future of the grid here in Australia. So please welcome Professor Dong.
Thank you. Thank you, Vic. Well, past 12, so good afternoon, everyone. Thank you for coming to the seminar. It's a great honor, and thanks for the opportunity to share some of our research here. So from the title, it's high-level talk about the power engineering research from power system to smart grid, future grid, and to future energy grid. Bearing the hat of head of School of Electrical and Information Engineering, very quickly, this is what the school does at the University of Sydney, and the logos are from the companies which are collaborating with the school and being part of the foundation of electrical and information engineering at University of Sydney. So we work on power, telecom, big data, biomedical, renewable energy, and fiber optics, and have major collaboration with vendors, utility companies, and government. So the content of my presentation today, as I mentioned earlier, first time here in this school give the talk, so I will make it a sort of high level, but I will give one example with reasonable level of details. So quick overview of power system research, and I'll show the roadmap, different research from power system to smart grid, future grid, energy internet, and with conclusions on opportunities and challenges in this area. In power engineering research, more specifically, we work on power systems engineering. So from power systems, starting from modeling of the system, the dynamics of the system, control of the power system, security or stability assessment, then coming to mathematical problems of deterministic security assessment and probabilistic security assessment. Then coming to power system economic dispatch. This is mainly how to dispatch generators to meet the demand in a power system. Then power system planning. My former role, I worked in task networks or Transpower as system planning manager. So for planning, you need to look after planning, stability, modeling, economics, cost-benefit analysis, legal, environmental, and many other things. So this is the most comprehensive research domain in power systems engineering. Then coming to recently, demand side management, energy storage, dynamic line rating. This can be regarded as power systems research and also smart grid research. Then we also, I don't want to read all of them, also opened condition monitoring in line with dynamic line rating. This is because of the asset in Australia and many other countries are getting old. For example, in Ausgrid, the 132 kV cables are very old, so that when doing operational dispatch, they have to be derated by 25%. If we have this rating, and we know the condition of the cables, that will be a huge saving on asset. Then in renewable energy, I understand this is School of Renewable Energy. I don't want to talk too much on the renewable energy itself. What we do is on grid connection of renewable energy. For example, wind power, how can we design wind farms? What we did wind farm is a typical project is to design an offshore wind farm for Hong Kong Electric, including forecast, stability assessment, reliability assessment, power quality, backup generation, and so on. Then also grid connection for other typical generators in the system. In view of funding, we work with heavily involved with industry, including all the transmission network service providers in Australia, some of the distribution network service providers here, AEMO and utility companies in Asia as well, and also SPREE in USA. They provide funding support for different projects. Then I move next to smart grid research. We formerly my role and Professor David Hill's role, Ausgrid chair, so we work for Ausgrid providing R&D support in smart grid, smart city initiative. And this list of projects are what we have been doing, have completed, a couple of them still ongoing with Ausgrid under the smart grid, smart city project, like distributed system design, OpNet modeling of smart grid measurement devices, real-time measurement, dynamic rating, grid computing platform for stability assessment, decentralized system, and load modeling. When I say load modeling, means load modeling at distribution level. Previously, normally when we say load modeling in power system research is modeling of the load at substation, aggregated load, but we look into models of load at feeder load. Then when we do the project, we observed the movement, shift of focus of the industry from the traditional power system control, reliability, telecommunications to peak demand and reliability. How can we reduce peak demand so that the investment can be deferred? Then the price of electricity on the bill should not be rising too fast. Towards recently, it's more about market efficiency, investment efficiency. How can we maintain the operation of the system with minimal or no investment, which I don't know how long that will last, but that's a trend. We've been hearing about big data analytics, and this is a great example from the smart grid research. The picture here showing a substation, distribution substation. Previously, for operation, we need only measure one output here of the feeder. Then the utility company are able to estimate the voltage, all the properties along the feeder, and do control operation appropriately for the last several decades. With smart grid, where the devices along the feeder, in the smart grid, smart city, there were 42 to 43 different devices, considered three-phase and different homes and appliances. So the information you got from previously one measurement can be hundreds more. You can imagine the data, and the measurement frequency, resolution of the data can be very high. Then we do need big data analytics, providing better understanding of the operation of the feeder. However, if our control is overly depending on so many measurements, then there will be risks of, if some elements failed, then there will be risks of system stability. So if I summarize so far until smart grid, this is also summary of our research of the research team with me and Professor David Hill over a number of years. So we started from power system, then from 1998, electricity market, which good to see in here. We work together in some projects. Yeah. So this and recently we do smart grid. As you can see on research side, we have optimization, modeling, computing platform, control these traditional research technologies. Then moving forward for industry, then we need commercial tools rather than just MATLAB. So we have all the commercial tools for power system analysis, for electricity market, and for telecom system modeling, for which a smart grid we can regard as the overlapping of cyber system with physical power system. So we need understanding and capability of modeling on both of the system. Then the interdependent, and they affect each other. So the interdependency between the two systems on top of the market forms a smart grid. And another research methodology is so-called complex systems. or I put topological analysis under complex system as well. So given the complex system of the cyber and physical system, what we can do, we can model the system like in weighted graph, then do graph analysis, which will improve the computational efficiency for very fast vulnerability or security assessment. Then you can follow detailed engineering assessment to get accurate answer. So given the roadmap, then currently we're focusing on what we call energy internet. The different terminologies here, some even refer to Internet of Energy or industry Internet of Things applied to energy systems. Then the energy internet links power system, telecom computing, and primary energy. So one of the technology could be useful is called power to gas. There are demonstration sites in Germany and other European countries and in China as well. So far still expensive, but the potentials are huge given that we have a vast amount of renewable energy which cannot be used because of the constraints in transmission network. However, if they can be converted into gas, then we have much better utilization of renewable energy. So actually I already mentioned the roadmap. Just to summarize here, I also use this in our open days to school kids, right, to show power engineering is not just working in pulse and wires or heavy machines. We're also working heavily on computing system. See, on the bottom is a screenshot from the Smart Grid Smart City GUI for smart home control and demonstration. The left two graphs are the traditional what we call power system blackout in 2003 in Northeast USA. So the moving is from grid power system, smart grid, future grid, energy internet, and the research and engineering focus moving from pure power system to telecom, ICT, computing, situational awareness, human factors, and more you can mention. I revised the smart grid structure from NIST and IEEE definition to form this model. You can see conceptual model to system architecture. Then there are three major architectures under the system architecture, namely power system architecture, communications architecture, and IT and computing architecture. Well, the comms in Australia in particular, we have NBN, then we have wireless communication for the last mile communication. And power system is what we have, whatever we have, generation, transmission, distribution, loads, and so on. IT computing architecture is the enabling technology to enable different applications hanging below the three structure. For example, different voltage control, electric vehicle control, and we can even extend this to water system, to gas, to transportation, to health. Just like when you get an iPhone, you can develop applications to hook up into the next generation smart grid architecture. The economics was not there. I included economics here because every engineering project we need to do economics, and you have to pass the cost-benefit analysis and make sure the social benefits is greater. Otherwise, there's no point moving forward. This is actually links with pure distribution level smart grid to a much wider conceptual area. Very quickly, I'm sure many of you know the Smart Grid Smart City project, but very quickly from a perspective of Ausgrid Center of Excellence, which you also got one here at UNSW. So lead by Ausgrid, investment from the government. Government had $100 million for the project, and Ausgrid put another $500 million. And these are the main vendors involved in the Smart Grid Smart City project, and also City Council's transmission company, water, and universities, as well as CSRO. The beauty of the demonstration project is that this is a national demonstration project on smart grid technology, and Australia is perfect testing bed. You know, the standards in Australia is very high. If we pass, if we succeeded here, then it can be applied to many other parts of the world. If anything failed, the rest of the world may not necessarily know. safe testing bed. Then back to the power system side, this is what we call grid applications domain, more on power engineering, custom applications like demand side management. In one of the scheme, for example, in a very hot summer day, on selected customers, they may be offered to go to the shopping center with $20 or $40 shopping voucher, provided they switch off their air conditioning at home, right? Contributing to peak demand reduction. Then voltage and power factor correction, this is to do with reactive power control and voltage control. In distribution level, all the distribution faders, most of the stability of system problem are related with voltage. Then distributed storage, including storage from households and storage from substation. We're still working on the substation battery energy storage system for different purposes. Fault detection, isolation, and restoration. If you ever experienced a blackout at home, you may know you need to call Off-Grid or whatever other network company. And if they accept a number of calls, then they will send an engineer to have a look to identify where is the location and what's the problem. Under this fault detection, isolation, and restoration, given the measurement devices, so the operator will know immediately what's going on, where the fault is. Then 90 or 95% of the fault can be recovered in 5 minutes. Then they can send an engineer, depending on the distance, to that specific faulting location. Can be fixed in 20 minutes or 1 hour or 2 hours. So this is the best PR when Off-Grid set up the Smart Grid Smart City Community Center in Newcastle. Then there will be substation feeder monitoring, electric vehicle support, wide area measurement in collaboration with Transgrid, distribution generation support, and the interoperability of utilities and NBN. This is a service area of the project covering Sydney, Newcastle, Port Stephens, and Scone, the mining region, Hunter region. We're including urban area, heavily populated urban area, and a very typical town of Australia, which is Newcastle, and regional area in Scone, or Hunter region, with long, skinny feeder feeding major mining customers. And the feeder can be run as a microgrid, which means some of the mining customers, they have their own generation capacity. So during times of low demand, they can actually be disconnected from a grid, which allow for microgrid testing. On the bottom, photo taken from the smart grid testing lab close to Newington. So every smart meter, before being installed at home, any user location, they have to be tested, mainly for the comms, make sure they can send signal back to the control center. Otherwise, most of the expensive actually not coming from the meter itself, coming from installation, coming from sending engineers to fix any faulty meters. It's a very important thing. Then this application will fall into custom application, grid application, and energy resource management. As you can see, after every application, there's a telecommunication stream, then coming to data and evaluation framework. No wonder most of the investment, about half of the money spending on setting up the telecom framework, but they choose a wrong technology, which is WiMAX. They should be using 4G LTE, or just using Telstra public network. Now I'll give a number of examples on the smart grid research, starting from the basic one. Any engineering project, we need modeling, and most of the models are well established, except load models. So the team, we're working with load modeling for quite a long time, being part of the SPREE Advanced Load Modeling Technical Report, which is a standard reference for the research community and engineering community, and also contributing to measurement-based load modeling for SIGRI work group. This is another industry standard reference material, and we worked with, for example, Western Power, AEMO, Off-Grid on different load models, and the model built for Western Power still be used by operation and planning there. So this basic approach is that we taking the measurement from the system disturbances, then choose appropriate model structure, find out the percentage of steady state model and dynamic model, and get the parameters of each model, and back fit into the commercial package which are used by utility company for operations and planning purpose. And these are the objectives to see the DG impact, or more specific, solar PV generation impact on the feeder, peak demand reduction, wholesale price optimization, and voltage regulation, and to find out the correlation between the demand and PV generation, correlation between voltage and PV generation, and upstream impacts of existing PV systems. In this, the full report is available from Information Clearhouse, which the government gave all this data to my research center, and currently hosted at the University of Sydney. Free to download. If you couldn't find it, email me, I will send the report to you. Then another major research is electric vehicle. In Smart Grid, Smart City, this is part of the research, but in these slides, what I've shown is joint research with State Grid in China. They have a national scale EV uptake scheme, and the batteries are battery swap stations rather than individual charging batteries. So we're working with State Grid and Zhejiang University to design what will be the best location of the battery charging station, considering the traffic condition, the impact on the electricity network, and the existing locations of petrol stations as well for space purpose. And this is a multi-objective planning decision-making process, and we publish in Transaction and Power Systems. For DG impact research, mostly we need to consider all the different parts of solar PV generation, wind generation, energy, battery storage, and control, as well as operation. So we put all the research into one framework, and this is one of the publications we published for distribution company operation and measurement. It all starting from load forecast. We need to know the load in the future. Then come to price forecast, either through market simulation or through time series analysis. Then wind prediction and solar prediction. Having this information in advance will help the distribution company to do the distribution operations planning to minimize the risks or minimize the regrets if the predicted wind didn't happen, for example. And this is also part of the paper we published in 2003 in Attribute Transaction in Power Systems. The controls, we encountered similar questions when I presented the work earlier. One of the questions will be, see, there are controls for example, wind power generation. There are controls for PV panel grid connection, and there are controls for batteries as well. So the research still needed because the coordination among the different individual systems are still not there, or not ready, not optimized. So this is the research. We need a systems of systems approach to achieve the best outcome. Following Smart Grid, we're moving to Future Grid, which we work together under the National Flagship Project, and our team, we're working on power system stability as well as gas and electricity network co-optimization and planning. This is a map of the national electricity market on the eastern part of Australia, and the lines shown are the gas network, which has some overlapping geographical similarity to the electricity network, but not entirely the same. For example, no central electricity generation in North Territory, for example. But the rationale is that the gas network and the power network has many similarities. And in cases of energy supply, we could set up a gas generator instead of transmission line to meet the demand growth, and vice versa. AEMO, when AEMO was first set up, the AEMO did has a function or objective to do gas and electricity co-planning. However, the methodology, the considerations, and many other things you can give more are not ready yet. So we're starting the research, try to achieve a framework, which we did, combining the power system planning approach on the commercial software called PSSE and DigScalent, used by most of the utility companies here. So this model, these two software are used to model the power system, and we're using Plexos to model the electricity market and the gas network built into the market. Right? However, these two are still separate. Then we have another module which we did in MATLAB to model the interaction of the two systems and to image the overall two systems into one to find out the interdependence and interaction and do co-optimization planning. The report of this is available in, I believe, it's end of this month. So that can be done. So following future grid, another thing for future grid is that smart grid is focused on distribution level only, but we are not fully utilizing the renewable energy. For example, in South Australia, the wind energy are not being fully utilized because of the weak transmission system. So if we extend the smart grid or the smart concept into the transmission network on the national scale, potentially we have a much better level of utilization of the renewable energy to achieve emission reduction objectives. Then the next stage I'm going to talk is energy internet, or internet of energy. Three of the facts of energy internet. In US, you have the Freedom Project, which is similar in line with internet of energy concept. Back in 2012, EU already identified that energy internet is a major drive on the energy system development in the future. And Germany has a number of demonstration sites. One of the projects is e-energy, and Audi did have a demonstration site on power to gas technology. And there are several aspects on energy internet, including super grid concept, while our team are working on the more low voltage end. So in our regard, we think energy internet is smart grid plus other energy networks like gas network, thermal network in cold climate, right? When they are CHP power plants, based on the next generation ICT technologies like 5G, Internet of Things, and so on. And three key components of energy internet. Number one is wide area power grid internet and energy coordination and management. And number two is multiple energy conversion, power to gas, gas to power, thermal to gas, and whatsoever, and thermal energy recovery. The next generation Internet of Things and ICT technology. The research, we wrote a paper a couple of years ago, just last year actually, to define this framework. And the team is working on some of the energy internet project with one of the power companies overseas. So what we envision, we're thinking energy internet beyond smart grid will achieve three major changes. Number one is that the energy base will be potentially possible moving from fossil fuel energy as baseload generation to renewable energy, given the Internet of Things technology support. And also the ICT network currently is closed network for security purpose. With the cloud, with cybersecurity research going on, that could possibly move into open network, which will provide much easier control and monitoring. And also the control, given the big data side, or moving from centralized to decentralized. Otherwise, there's no option to achieve the control, given the huge amount of big data. Give one specific example how the energy internet can be benefiting the system operation and customers. This is a high frequency appliance level data and analysis. Right? The curve shown is from one of the a typical smart grid smart meter measurement from a particular user, showing the real power consumption. And from this curve, we can see a number of major appliances like refrigerators, aircon, oven, and you mentioned it, maybe pumps, maybe water heaters and so on. If you do switching one by one, very easy to identify. However, in most of the cases, they are mixed. So how can we extract this model from the customers without actually going to the home, do a custom survey? So detailed load prediction, load modeling, and we can build time varying load model, and we can capture the usage pattern of the household or any user. So aggregated profile is what we get from a smart meter measurement. This is one of the real meter measurement that you can see, quite messy, a bit difficult to identify what's going on there. However, if we do disaggregation, then we can separate different appliances within this meter coverage. Fridge, aircon, kitchen outlet, and dishwasher, dryer, and so on can be identified. Without actually intruding intrusive measures. So we call it non-intrusive load monitoring. Once we know the different appliances, we can group them. Some of the appliances can be controlled. We call they have higher demand response potential, which may interact with the grid, and some of them users don't want to be controlled, like a cooking top. By the time you're hungry, you want to use it. Don't want to delay the usage. But for hot water, it's already been controlled. Air conditioning can be controlled as well. Fridge, you can switch on, switch off, still maintaining the temperature. So some examples here. This example for monetary-based demand reduction. If we look at 10 households in a neighborhood and identify different appliances, the circle showing the customer number 3 using a lot of electricity for air conditioning. Right? So to reduce this electricity bill or to achieve peak demand reduction, most effectively look into the control on the air conditioning. This is for the appliances and also for the user. Now we can look at another application. Given any energy consumption, if we know the pricing scheme of the company, then we can build up a very detailed billing of your electricity bill component, showing you how much money you spend on any specific appliances, major appliances. Then you will know, well, say in this particular example, air conditioning is not the major cost in your electricity bill. However, the heater, water heater is most important here. Then maybe you may think of what I can do to get a more effective water heating services. Then that will be most effective to reduce the electricity bill. Rather than go randomly, you may spend heaps of dollars to aircon, but the achievement may be small. This is another example. You can compare your consumption of the same appliances with your neighbors, with other in the community. In this particular example, household 3 is spending too much money on aircon. It could be either he needs more services from here, or the model of the air conditioning could be old. So time to change for a new one. Either for the customer or for the energy company, maybe you got some recommendation of what will be the best brand of air conditioning and provide installation and support. Right? That's another business opportunity for the energy retailer. Then you can also identify what our users are using, group different users. So this group is grouped by dishwasher usage. That is very efficient in view of electricity and water usage. So you can do some marketing material based on this as well. Then to achieve this, what we use is called electricity fingerprint. This is not a new concept. It's actually started from over 10 years ago. Different appliances will have different signature. You can look into signature to identify the appliances. However, as we know that there are new technologies appearing every month, every year, so the signature changed significantly over the past few years. And this is some of the signature work published over 2010 until 2014. Based on the different representation, you can identify the users from the measurement. And this is an earlier paper which I can find from 1992 in view of real power reactive power consumption. Then you see the location of the signature of different appliances. With the energy efficiency improvement, actually they are all crowded towards the center of the coordinate here, which means they tend to consume less power. And this is useful for dispatch as well, because you will know real power as well as reactive power consumption. Even though you only know real power from bill, but you can know from the signature estimate the reactive power consumption as well. But there are limitations there. One of the major limitations is some data sampling rate, and they may not be available for current smart meter infrastructure. For example, for power quality related measurement, to obtain those things, you need 8,000 Hertz resolution for measurement, which is almost impossible for smart meters. But we still want to achieve the outcome, so we need new technology, and also the huge data requires very expensive storage and data maintenance, which make it impossible as well. Right, that's one example. Aware of the timing, so I give another commercial example, what we call energy internet, why we're doing the research. I took the data from China. As you know, that State Grid is the largest power company internationally, right? And China Southern Power Grid is also very large, supplying southern China. So this is a consortium over there. They work on energy internet, and a estimation of the potential in market is $1 trillion US dollar. This is US dollar published in the US media. There are heaps of business opportunities, ranging from renewable energy, from power system, from ICT, and to e-commerce, to even expand to health, other critical infrastructure, and data, not mentioning that. So this is basically Industry 4.0, and we focus on energy to do the energy internet. Then coming to conclusion, challenges. The power system today is no longer a single system. As I presented earlier, it interacts with other systems. And to achieve optimality, we need a systems of systems approach. So we may have individual DJ, but we need to study the interaction among them, and we need to study the interaction and the interdependency between the physical system and the cyber system, and economics as well. So renewable energy can be contributing more to emission reduction if supported by a stronger network. I attended a Clean Energy Council meeting earlier this year in Melbourne. Very pleased and to identify that they finally recognized the need for investment into the network. Because for the past few years, most of the thing is that overinvestment in poles and wires. However, to really achieve the benefit, we do need a strong network. And one of the consulting company in US, I forgot which company, saying that the network need to be doubled to accommodate the renewable energy target here. Then efficient energy market is also required, and energy storage, big data analytics, Internet of Things and other things, if I summarize them into the so-called Internet of Energy or Energy Internet, will be one of the most effective approach to provide a solution for and achieve the objectives of energy industry. Thank you.